Hi mga may kailangan, it's Mekalalongan Manguni from Bachelor of Science in Psychology Section 2A of Cotabato State University. Welcome to my vlog, and for today's video, I'm going to discuss the last two parts of Chapter 11, which is the controlling within subject designs. Before we proceed to the discussion, let me tell you the objectives of my report. First, we have to learn about design in which subjects participate in more than one experimental condition. Number 2 is to understand the pros and cons of within object designs. Number 3 is to learn how to control for problems specific to this design. So in controlling within subject designs, we have what we call controlling for order effects, which is the counterbalancing. So what is counterbalancing? Counterbalancing is a technique for controlling order effects by distributing progressive error across the different treatment conditions of the experiment, may also control carryover effects. So I downloaded a video, guys, to discuss what is counterbalancing for you to be able to understand. So watch it.
One of the biggest problems we have within subject designs are order effects. Because we're repeatedly measuring people, we have to be very careful about what order in which we might measure participants. So the first issue we have are practice effects. Practice effects occur because subjects just simply get better at a task after repeatedly engaging in that task. So they've practiced at it, so they're going to get better at it. And it really depends on the task itself. People tend to not get much better at episodic memory tasks, for example, because their memory is their memory. But if it's something that's a little bit more skill-based, like sequence learning or mental rotation, they will definitely get better as they have more practice with that kind of task. So you have to think very carefully about how you might order your independent variables. So for example, there is a phenomenon known as the Mozart effect. And if you play Mozart prior to participants engaging in a mental rotation task, they get better. Well, in that instance, you have to be very careful how you order your experiment. So in that case, we would counterbalance, which we're going to talk about here in a minute, the order of whether or not they get Mozart or they sit quietly for a few minutes, or maybe some other kind of music, depending on how we set up the experiment. But we would want Mozart to occur first in the order effects for half the participants, and second for the other half of the participants, so that we have counterbalanced the effect or the potential effect of that practice on that kind of task. Similarly, we can have carryover effects. Carryover effects can be positive or negative. So practice effect is where people are getting better. But a carryover effect is when performance on one task can benefit or inhibit performance on a subsequent task. So it might be these are two different tasks. So in fact, the Mozart effect is actually what we would call a carryover effect. That is that listening to Mozart has carryovered to that mental rotation task. And so we would call that a carryover effect. This can occur between two different tasks simply because of the way in which we might end up with some sort of semantic priming, or we might end up with people that are getting better at numbers, but that interferes with something else. And so we have to think very carefully about how we might get these kinds of carryover effects. In an extreme example, some of my research involved pharmacologically induced amnesia, or drug-induced amnesia, using a drug called midazolam, or Versed. And so our participants came in twice and received an injection either of midazolam or of saline placebo. Those participants that received midazolam in that first session, that is, that drug-induced amnesia, in the second session, they were much more likely to rate their memory as being worse than participants who had saline in the very first session. So that kind of carryover effect is an important thing to think about, and again, that's why we counterbalance. Fatigue effects are sort of the backwards part of a practice effects. Depending on how long an experiment is, participants will just get tired of being in it. If particularly it's a lot of trials of the same thing over and over and over again, people get pretty tired of it. And so they get fatigued, they don't pay as much attention, they're not putting as much effort. So we have to be very cautious with that as well. So their attention might wander. So we don't want performance on that sort of last task in the experiment to suffer simply because it's last. So again, we counterbalance for order. And so what we're doing when we counterbalance is we're trying to distribute those effects evenly. So practice effects are distributed evenly across conditions. Fatigue effects are evenly distributed across conditions as well. So that's what we have with order effects. When the order of the levels of our independent variable or of different tasks, depending on the kind of experiment we might have, is going to have an influence over our.
Next to that, we have what we call subject by subject counterbalancing. It is a technique for controlling progressive error for each individual subject by presenting all treatment conditions more than once. Next, we have ABBA counterbalancing, a technique for controlling progressive error for each individual subject by presenting all treatments conditions twice, first in one order, then in reverse order. In reverse counterbalancing, they use ABBA procedure works to balance out the effects of progressive error. So for you to understand what reverse counterbalancing used in subject designs, I downloaded a video that will explain how ABBA procedure works.
So that then gets us to ABBA counterbalancing. It's not ABBA counterbalancing. It actually stands for ABBA. It's very similar to block counterbalancing, but with only two conditions. So what we do then is this allows for no more than two conditions of the same instance in a row. So we'll go ABBA, ABBA, ABBA. Pretty simple. The idea is, again, so that A always comes before B always comes before A, and it always does so in the same number of instances. So we can distribute any practice or fatigue effects across the experiment. Pretty straightforward. Now,
next one is block randomization, a method assigning subjects to treatment conditions in between subject design. So I downloaded a video to know how this method is being used in controlling within subject designs.
Block randomization. So this procedure is used whenever we have a large number of repeated occurrences of an experimental condition. So for example, if we were going to direct people to study items based on their structure, that is it upper or lowercase letters, based on its acoustic sound, that is, does it rhyme with another word, based on semantics, does it fit into a sentence, and self-reference, does this word apply to you? So there could be four different ways in which we might get people to encode individual words. So is it upper lowercase letters? Does it sound like or rhyme with this word? Does it fit into this sentence? Or does it apply to self-reference? Four different encoding conditions. Well, we might have then 25 of each of these, so 100 words. So in order to see which one might be the best way for us to remember. So what we can do then is we can assign sort of letters, easier structural, acoustic, semantic, and self-referential processing. And then what we can do is sort of randomize within each block. So each chunk of these four different types of encoding will occur together. There'll always be four of them together, but what order they occur within that block will be randomized. So just pseudo-randomize these. You can do this with a computer. It's pretty easy. But here we have A, B, D, C, B, A, C, D. So each one of these individual conditions is occurring within a block. So each block will contain n number of trials, where n is the number of conditions. We have four levels of our independent variable. We have four trials within each individual block. We'll create then k blocks. This will be the number of times each condition is completed. So in the example I was just using, we would create 25 of these blocks across our 100 item experiment. So 25 self-reference, 25 semantic, 25 acoustic, 25 structural. We're going to block randomize those so that we don't end up with 10 structural random, 6 self-reference all the way to the end. We've evenly distributed these trials across that 100 item list so that the first 4 items include one of each condition and the last 4 items include one of each condition. So the idea here is, of course, to distribute the effects across that list so that we make sure that we don't have practice effects or fatigue effects for any one of these 4 conditions. So that order of conditions is randomized within each block, and then we'll have 25 blocks, each with the 4 different conditions. So each block will contain each level of our independent variable, and and then we will create however many blocks for the number of times we repeat each condition. Okay.
We also have what we call the cross-subject counterbalancing, used to distribute the effects of progressive error so that if we average across subjects, the effects will be the same for all conditions of the treatment. Next one is complete counterbalancing, a technique for controlling progressive error and all possible sequences that can be formed out of the treatment condition and using each sequence the same number of times. Last but not the least of the part of counterbalancing is what we call partial counterbalancing, a technique for controlling progressive error by using some subject of the available sequences of treatment conditions. In partial counterbalancing, they use the procedure the mean square technique, in which a matrix of square the sequences is constructed so that each treatment appears only once in any order position. To further understand how square Latin was being used, watch these videos.
We go to what Latin squares. I actually found this really nice color representation of what a Latin square counterbalancing looks like. The goal here is to ensure each condition comes before and after every other condition. So here we can see red comes before orange, red, the red comes before all these conditions, the blue comes before. Counterbalance carryover effects across the entire. So formally, a Latin squares design is an array where each condition occurs exactly once in each row and once in each column. Now, we're going to have to get into, and we're going to gloss over some of the math involved. This is actually an incomplete Latin square. So it's actually a reduced form of a Latin square because it has an odd number of conditions. What we would do in the instance of an odd number of conditions, we would create a second array in which we start with that first row, but we reverse its order. We'll get into that here in just a second. So, here's how we construct a Latin square. The easiest thing to do is to think of this with numbers. We assign each condition a number. We start with the initial order 1, 2, 3, 4. Then we just add 1 to each, and then whenever we get to n plus 1, so n is our number of conditions, that will equal 1. So when we get to 4 plus 1, that becomes a 1. So here we have 1 becomes 2, 2 becomes 3, 3 becomes 4, 4 becomes 1. You can see we then have an array in which this occurs in each row, and we end up with a number of 1s in each row. Now, to do this completely, we are going to do the same thing with an odd number. We start 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5, 1, 3, 4, 5, 1, 2, etc., etc. But with an odd number of conditions, to make sure that we have truly evenly distributed
hey kids, give me thumbs up if you like the video. Also, don't forget to subscribe for more videos.
Where we take the first row and reverse it. We're going to flop down. Sorry,
Bye-bye.
Bye-bye.
Flip down and reverse it. So we're going to do this 5, 4, 3, 2, 1, and then we do the same thing we did before where we add 1 to each of these. And when we add 1 to 5, we go back to 1 again. And so we have everything distributed evenly again. So with an odd number, you're supposed to construct 2 Latin squares, so it would actually take 10 participants to get a complete counterbalancing for an experiment with 5 conditions. So that's constructing a Latin square. I want to run through some pros and cons of within subjects designs. We'll start with the benefits. Fewer participants are needed because we're doing everything within subjects, whereas when you do between subjects, you need a number of people in each condition. We'll talk about that in the next lecture. Solves the problem of individual differences. We got one group of people, so we don't have to worry about if there's more males or females, or people are more educated or less educated, or what they had for breakfast. And finally, we get better statistical power out of within subjects designs, and that's because we're able to account for the variance, the shared variance between measurements that is associated with the individuals. We'll get into that here in a sec. Problems with within subjects designs. Basically, we have to think about practice effects, carryover effects, fatigue effects. And then finally we have this problem of differential transfer. And this occurs when we can't, something about one condition will poison or make it impossible for the next condition to be run the same way. So, for example, if we are using an incidental learning paradigm where we haven't told individuals that they are in a memory test, so we're going to do intentional versus incidental learning, that is a problem of differential transfer, because in one case they're going to learn incidentally, we're not going to tell them they're in a memory test, and then in another condition we're going to tell them they're in a memory test. Well, we can't counterbalance that, and so that's tough to do within subject designs. Other times you really can't transfer from one condition to the other. So for example, in the smoking cessation literature, we can't transfer someone from one smoking cessation attempt to another, because essentially we want people to quit smoking, and they can only quit if they're going to quit, they're going to quit, or they're not going to quit. And so we can't do those as within subject designs.
Since I'm done discussing the counterbalancing, let me show you the tips or the question for you to be able to know to choose your design. First is, you need to think about the hypothesis of the experiment. Second one is, how many treatment conditions do you need to test the hypothesis? Third one is, would it be possible to have each subject in more than one conditions? Do your treatment conditions interfere with one another? Consider the practical advantages of each approach. You should do that. And last one is, you must remember to review the research literature, because it is important to know the history of your topic. So that's the tip and questions. So to be able to choose a design, or for you to be able to know how to choose your design. So that could be all. Thank you for watching my vlog for today's video. I hope you learned something new. Bye bye.